Good? Okay. Alright guys. Well, some of you guys left. I guess the drop deadline passed, so you're all watching at home now. Alright, so as always, I've waxed too eloquent on Eigenvector problems, and we're going to be a little bit behind the schedule that's on the course website, but that's okay, because like I keep saying, I built in lots of wiggle room toward the end of this class. But I know that about 75% of the people here are only here for like the last 2 days when we talk about fluid simulation, because apparently that's the most exciting thing you can do in computer graphics. And so I'll be sure to hit that topic for at least a lecture. Right, so anyway, your homework is due on Monday. I think next week we don't have homework. We have a midterm that the Monday or Wednesday after that. But I'll try and post, some midterms from past offerings of CS205. Obviously, this class is somewhat different. I'm sure you discovered that by now. But the content is the same, and we're more or less following the same schedule that they did. Believe it or not. Are there any procedural questions or anything before we dive into today's, nightmare material? No? All right. Without further ado, we're going to have our last and final day of Eigenproblems, although we're going to do a couple things related to it, and then we're pretty much done with numerical linear algebra. When I say done, of course I'm completely lying, because it's going to form the basis for everything we do for the rest of this class. But conveniently, your midterm is coming up, which means that by the time we do the rest of this class, you'll have already studied all this stuff and will remember it a little bit better than you do now in lecture. Do you have a question? Is your hand? Okay. No problem. No. If that's comfortable, go for it. Okay. So as always, the last 5 minutes of my lecture last week were pretty much worthless. And so today we're going to go back and actually prove that this magical QR iteration method works. It's great talking about this because we have the peanut gallery in the front row here, and every time my math gets a little bit fuzzy, I can see all these furrowed eyebrows, and I know that I'm going to have to cover it again in the next lecture. And that is certainly the case today, so we're going to go back and completely understand this algorithm. So if you recall from last week, we did this experiment that was just way too tempting not to figure out what it was telling us about life. Right? We said, okay, we know that conjugation, right? Like if I take a matrix A and I pre-multiply by the inverse or something, I post-multiply it by the matrix itself, then I haven't changed the eigenvalues. And we decided, okay, well that's great because we can conjugate away on A without changing the eigenstructure, and this somehow seems like a good strategy for trying to reveal the eigenvalues of the matrix. Yes?
Was A any matrix, or is there something special?
For now, A will be symmetric. It turns out that you don't need that, but for our proof today, we're going to need it. And that's part of what I was missing while I was dabbling in the class. Anyway, so we said, okay, conjugation preserves eigenstructure, and so somehow we want to conjugate with something we think is related to the structure of A at least, and so one way to do that would be to QR factorize A, and then just conjugate by that matrix Q, because Q is orthogonal, and somehow Q inverse is easy to write down. Not somehow. Q inverse is Q transpose, so it actually is easy to write down. Yeah? And so the experiment was, well, what happens if we just, for fun, decided to do this? And in fact, QR, when you write A is equal to QR, and when you conjugate this with Q, you get RQ, and this is like too attractive of a thing not to play with. Right? And in fact, I claimed that if you iterate this, eventually you'll reveal the eigenstructure of A. And in particular, what's going to happen, at least when A is diagonal, or rather, if A is diagonal, you don't have to go to this one. And when A is symmetric, is that this is going to converge to a diagonal matrix where the diagonal is actually the eigenvalues. By the way, the second half of that sentence should be unnecessary, right? Because if I have a diagonal matrix, his eigenvalues are obviously the numbers of that. In fact, you proved this on your homework, sort of, when you talked about upper triangles. Right, so our algorithm is A1 is equal to A, and then we're just going to iterate, we're going to factor AK into QR, and then we're going to define AK plus 1 to be RQ, and then just keep playing this game until convergence. Yeah? And then last time we said, okay, well what happens if we converge? Well, if we converge, then assuming that our QR factorization software is somehow consistent, we expect that QR equals RQ. By the way, you should consider everything from here till the end of this little deck of slides to be kind of an intuitive argument. There are going to be a lot of analytical little boundary cases that I'm going to ignore. So I'm expecting furrowed eyebrows out of YouTube, but that's okay. because it turns out that these are actually not big issues. But I don't want to have to talk about upper Hessenberg forms and all these kinds of things. Anyway, so ignoring all of that, if we converge, we expect to reach the matrix A that satisfies that A is equal to QR, and then like if we were to do an extra iteration, right? Factor A is QR, multiply get RQ, you get the same thing back, right? Because somehow you reached a fixed point. And the question that I left you guys with at the end of class, or tried to kind of intuit but didn't do a very good job, was why is this enough to show that our algorithm should reach something interesting if it does indeed converge? And to do that, you can ignore the proof on the bottom. This is mainly for me because I keep getting it wrong, so I wanted to put it there. I tried to boil it down to the simplest possible fact that is rigorous, and I came up with the thing on the top of this slide. By the way, if you search for proofs of why QR iteration converges, it's like one of these funny things where all these textbooks cite other textbooks because they're too lazy to figure it out. And it's actually quite a challenge to find somebody that has worked this out in detail. So anyway, we can work out this special case where I'm going to assume two things about our matrix A. One is that he is symmetric, right? And what does that mean? In particular, it means he has a full eigenspace, right? His eigenvectors span Rn. We spent a lot of time talking about that in section or in office hours this morning. And the second thing, and this is what I was missing on Monday, is that A has to have unique eigenvalues. This is an extra little twist. By the way, it turns out this twist can be relaxed. In fact, if basically what you can do is perturb A a little bit so that he has unique eigenvalues, apply this argument, and then show that it still holds in the limit as your perturbation gets small, but that's kind of complicated for a class like this. So anyway, let's suppose that, maybe I won't copy the statement of the lemma down, but we'll do the proof on the board. Let's say, suppose that A is equal to QR and is equal to RQ, then, and that A has no repeated eigenvalues, then I claim that A must be diagonal. Right? And thus we're kind of done. Yeah? And let's do this proof in detail because it's kind of slick. Alright. So first of all, let's take any eigenvector x. Take an eigenvector, we'll just say evec x. So that says that ax equals lambda x. Hopefully you're with me so far. Alright, so what are we going to do with this thing? Well, I'm gonna do something kind of tricky. I was happy with this at like 3 in the morning yesterday when I thought of it. So, I'm going to multiply both sides of this expression here by the matrix Q. I'm also going to swap the left and right hand side just for yes. So, we get lambda qs, right, because I'm just multiplying both sides by q, equals qas, right? And now, we have an expression for A. By the way, I'm going to drop all these infinity subscripts. Is that cool? Cool. So we know that A is equal to QR, right? Like that. Right? But we know that QR is equal to RQ. So let's swap these guys. And what you're going to get is QRQS. Okay. Now, we were talking about this in office hours this morning. There's like about 5 tricks in linear algebra that I just repeatedly apply in this class, and this is going to be one of them, where you see I've grouped it like this so far, but now I'm just going to group things the other way, right, and group the left 2 guys. But look at that, that's QR again. So in fact, what I just showed you is that this thing is equal to A times QS. Cool? So what did I just prove to you? I proved to you that not only is x an eigenvector of A with eigenvalue lambda, but also Qx is an eigenvector of A with eigenvalue lambda. Now here's the thing. If I assume that all of the eigenvalues of A are distinct, right, then in particular this means that the eigenspace corresponding to this value lambda is spanned by one guy. Yeah? So that means that Qx has got to be parallel to x because there's only one eigenvalue vector with this eigenvalue. Now we also know that Q is orthogonal, meaning it preserves lengths of vectors, right? So in fact, all of this together implies that Qx is equal to plus or minus x. Isn't that slick? Now here's the thing. A is symmetric, so he has a complete eigenspace. Right? So these vectors x span Rn. And we know that Q, now, on every vector that spans Rn, can at most flip its sign. This, if you think about it, is enough to show that Q must have, and I'll let you kind of think about this home, this diagonal structure of just like +1, -1, +1, you know, just plus or minus 1 all the way down the diagonal and 0 everywhere else. Yeah? So finally, how do we complete this proof? Well, we know that A is symmetric, and we know that A equals A transpose. So we know that A equals A transpose, right? In particular, right, this says that QR equals, R transpose, Q transpose, right? Just by taking the transpose of A on both sides. But this matrix is diagonal, right? So in particular, the sparsity pattern of QR is the same as the sparsity pattern of R, right? The places where it's 0 are the same. And same goes for R transpose, right? So this thing, so where can this guy have zeros? Well, R must have zeros. So R is upper triangular, right? So that means what? That means that the lower half of R has to be 0. But I transpose that here. But since they're equal and they have the same sparsity pattern, in fact, R is diagonal. And since A is equal to QR, it's the product of diagonal guys, and my proof is done. So what did I just show you guys? I showed you that if QR iteration converges, I haven't shown you that it converges, by the way. But if it does, and A is symmetric, and A has unique eigenvalues, then in fact, what it must converge to is a diagonal matrix with all the eigenvalues of A. Okay. So there's a lot of tags there, but such is life. It turns out that if it has a repeated eigenvalue, this process doesn't have to converge, but what happens is the R matrices have a special structure that lets you read out the eigenvalues regardless, but that's a little bit complicated. Cool. By the way, so it converges to a diagonal matrix. Why do we know that the eigenvalues of that diagonal matrix are the same as the eigenvalues of the A that we started with? This is humongously important. Well, remember what our iteration was doing, right? We're really just conjugating A by Q a bunch of times, right? So every time we do that, we haven't changed the eigenvalues of the matrix. That's what similar matrices do. So in fact, in the limit, we also keep the same eigenvalue. Okay. Oh man, am I tired. Okay, so right. So our last step is to see like, okay, so why should we expect this thing to converge, right? I mean, so it is already kind of magic that if it does converge, it gives you eigenvalues. Like this is like in case you haven't absorbed my enthusiasm, you should know that I really like this algorithm. But there's actually kind of some reasonable ways that you might argue that this thing converges. So one way is to look at the powers of the matrix A to the K. Right? So I can take A and just keep multiplying it by itself a bunch of times. Right? And this sort of looks like our power iteration method. Yeah? In particular, I claim that A to the K is equal to A times A to the K minus 1. Yeah? Or actually, I guess I factor the other way. A to the K minus 1 times A. Yeah? Now, why the heck would I do that? Well, I can write the columns of A, right? I can write A in this form. A1, AN, yeah? And now if I pre-multiply this thing by a matrix, it's the same as multiplying each of these vectors by that matrix, right? So in fact, what I've done is I say, okay, A to the K is really the same as taking all the columns of A and multiplying them by A to the K minus 1. This is a weird way to write it, yeah? But what does this buy me? What do all of the columns of A to the K look like as A gets big? Remember how power iteration works? I keep hitting some vector with the matrix, right? And if I hit it with that matrix enough times, it starts to look like the biggest eigenvector of that matrix. Well, yeah, so the vectors A1 through AN are very special vectors, but they're still just vectors. And when I hit them with A enough times, they all start to look like the biggest eigenvector of our matrix A. Yeah? So if I take humongous powers of A to the K here, as K gets big, this thing just looks like a bunch of columns that are all parallel to the biggest eigenvector. Yeah? Now here's the trick. What if I do Graham-Schmidt on the columns of this matrix? So we answer the first question. What happens if I do Gram-Schmidt on the columns of this matrix? Well, remember how Gram-Schmidt works? You kind of start with the first guy, you make him unit length, and then you project him on the rest of the guys, and then you iterate, right? Well, does this make sense? Does this make sense, Gram-Schmidt? Remember this one? Somebody raise their hand, please. You make me sad. Still only happy with this. Is there a question I can help answer? Do we remember Gram-Schmidt? Let's think about it. So remember we have a bunch of vectors, and we want to orthogonalize them. So how do we do it? We take the first vector and just leave him alone. And then we take the second vector and just project the first guy out of him. And we take the third guy and project the first two out of him. Right? That's Gram-Schmidt? Now we're okay. Okay. So it's my first time teaching. You gotta help me out. Okay. Right. So what happens if I do Gram-Schmidt to this matrix? Well, the first thing that happens in the first column, what happens? Well, I just divide him by his length, right? So the first column is a unit vector parallel to some big power of A times a vector. So the first column will look like what? Yeah, exactly. The first column of this guy, if I do Gram-Schmidt, is going to look like the biggest eigenvector of A, right? Because this, right, this number, a to the k minus 1 times a1, right? Remember how power iteration works, right? I just hit a, or any vector for that matter, with a matrix enough times and it starts to look like the biggest eigenvector. So in particular, as k gets big, the first column of this guy is parallel to an eigenvector. Yeah? So now I continue Gram-Schmidt, and now I'm going to project this first eigenvector out of all the rest of the guys. So what does the second column look like?
It looks like the epsilon, and then you have to divide it by like...
You have to divide by the length, but that's not a big deal.
But I mean, the problem is if all of them are almost the eigenvector, then if I project out like my first vector, my second vector, of like epsilon, and then if I divide by that...
Oh, you're absolutely right. This is numerically a horrible way to go. This is a pedantic
happens?
exercise. This is not the way to actually find eigenvectors. I'm going to bring this back to QR iteration in a minute.
Okay.
Right. So yeah. So if the first column starts to convert, so as I do QR factorization or particular Gram-Schmidt on this guy, right? The first column is going to start looking like the first eigenvector. The second column, well, it's going to look like a to a big power times some vector with the first eigenvector projected out of it. And if you remember from last lecture, that gives us the second eigenvector. Right? So in fact, if I do QR iteration on this matrix as k gets big, or rather if I do QR factorization on this, the columns of Q are going to end up looking like eigenvectors of A. Isn't this like... No, you're right. I forgot your name. I'm sorry.
Joe.
Joe. Yeah, Joe is right. This is numerically a horrible way to go, right? I mean, if we're multiplying huge numbers of things, and they're all going to look like the biggest one, and then you're just going to have epsilon left. But you know, if you could somehow do infinite precision in arithmetic, this would converge and be well behaved. So I claim that in fact, a to the k is equal to the product of all the q's that you've gotten along the way while you're doing this QR iteration, times the product of all the r's. Let's prove this. We can prove it inductively. So, first of all, in fact, we're probably not even prove inductively, we're just going to do a few steps, and then you can probably see the rest. So, A1 is equal to Q1R1 by definition, right? This is how we factored in. Yeah. What was A2? Well, we defined him to be Q2R2. Let me get out my notes to make sure I do this right. Oh, I'm sorry. I was doing the wrong proof. So what is A squared? Well, it's Q1R1, right? Because this is A times itself. Okay. But now, right, we're going to apply one of like the two tricks we know how to do in CS205, and that's we're going to say, well, this thing is the same as Q1R1, Q1R1, right? All I did was group it differently. But remember, this is exactly how we defined A2, right? Remember our QR iteration, we factor QR and then we replace it with RQ, so this is A2. And then, in the next iteration, we factored this guy, right? So in fact, this is Q1, Q2, R2, R1. Does everybody see what just happened there? This is kind of tricky. right? So I computed a squared by just multiplying a by itself twice. And then I grouped the middle two terms, and that looks like RQ. But remember, our QR iteration is exactly computing QR and then multiplying RQ to get the next iterate. Yeah, so that's A2. But then, after that, we factor A2, right? And we factor him as Q2R2. Yeah. So in fact, you can repeat this argument, and in the end, you get this expression up here. Right? Now, as we all know,
Was that from last lecture where it says A2 is equal to R1 Q1?
Yes.
Okay.
So our iterative scheme, remember, is A1 equals A, right? And then A K, we're going to factor him as QK RK. And then A K plus 1 is equal to R K Q K. Hopefully I've got this easier. Yeah. So effectively our algorithm is factors QR, replace him with RQ, and iterate. Super simple algorithm. I really like this algorithm. Okay. So anyway, what does this tell us about life? Why do we care? Well, so we now have a QR factorization of a to the k. Right? Because the product of a bunch of orthogonal matrices is still orthogonal, so the product of all the q's is orthogonal. And the product of upper triangular things is upper triangular. You showed that on your homework. Yeah? So in fact, we secretly have been computing a QR factorization of a to the k for big K the whole time. Yeah? In fact, one way to get the eigenvectors of your matrix would be to just carry around the product of all these q's as you do QR integration. Yeah? Because remember that the A is going to converge to just a diagonal matrix. So, how does the proof of convergence kind of go? I'm only going to sketch it out because it gets a little hairy. But basically, you can say, okay, so a to the k, right? We've decided that as we take k to very large powers, this q starts to converge to the matrix of eigenvectors, yeah? Which means that q sub k up here can't contribute a whole lot, right? That is, the product of q1 to qk minus 1 looks an awful lot like the product of q1 to qk. Because as k gets big, both of those just look like eigenvectors. Again, I told you this was a fuzzy proof. But if you believe that, then that means that qk is slowly converging to the identity matrix, right? Because it's not doing a whole lot to this q matrix. Yeah? And then remember that our alternative way of thinking about this QR iteration is by, all the way back here, right? Just conjugating by q. So eventually we're just conjugating by the identity matrix. Yeah? So that means the A's have got to converge too. So vaguely, that's the argument that shows convergence. Yeah, the front row is looking furrowed, but that really is actually how you formalize all this. And in the end, you can show the QR iteration convergence in a lot of special cases. And it gives you exactly what you want in like 4 lines of code. Cool. So anyway, that's enough of that. This is an example of a Krylov subspace method, which is outside of the scope of CS205. Beyond this, the idea of Krylov subspace methods is that you keep track of, rather than just doing power iteration, you actually keep track of the last couple iterates of power iteration. Right? So maybe you have b, ab, a squared b, all the way up to a with k minus 1 b. Right? You actually keep track of all those guys and orthogonalize them. Right? And by a similar argument to what I did with the a, you can show that this can get you more than one eigenvector at a time. And there are lots of different methods that do this. Your book sketches a few of them. The Wikipedia page is also enlightening. But anyway, so that kind of concludes our discussion of how to compute eigenvectors. Right? It's one of these fun areas of math where the proofs are really a little bit hairy, right? Like we have to be very careful how we handle this. Obviously I wasn't, but hopefully you get some idea of how this goes. But even though the proofs are a little hairy, the algorithms are super simple, right? Like power iteration, you just literally matrix vector multiply over and over and over again and eventually get an eigenvector out. This is easier by a long shot than Gaussian elimination or some of these other things. Cool. So, following our usual pattern in CS205, we first talk about applications, then we talk about how to solve the problem, and finally we have to talk about conditioning. Yeah? By the way, I'm going to relax this when we get to the nonlinear stuff because I'm a human being. But let's talk about conditioning of the eigenvalue problem. Right. So, and you can start to see why we're not going to give quite as vigorous conditioning proofs because they get really hairy the more complicated these problems get. Right? We're slowly stepping up our game in this class. But in particular, one question you might ask is, if I perturb the matrix A a little bit, right, then what happens to the eigenvectors and eigenvalues of A? This is a classic perturbation problem. By the way, this is an entire area of math theory, right? The math theoreticians are very concerned with assorted perturbation problems, but these are very simple ones. So, the question you should ask at this point, obviously this is kind of a hairy expression up here. What are the independent and dependent variables here? Okay, like what is the experiment I'm trying to examine? Well, when I talk about stability of eigenvalues here, what I'm really saying is if I perturb my matrix A a little bit, what happens to both the eigenvalues and the eigenvectors, right? So in fact, our independent variables are sort of A and delta A, and everything else is a dependent variable. Okay? This is kind of an unhappy case, right? You have 1, 2, 3, 4, 5, 6 different things that can all move around all at the same time. And this is why you can probably see that perturbative analysis is really quite hairy. In this case, it isn't so bad. So, all right, so let's jump right to it. Okay, we're going to make an approximation, and let me justify why I can do that. So, I'm going to multiply out the left and right-hand sides of the expression you see here. Right? And in particular, what I'm going to get, which I don't know, right here is we get AX, right, for the first two. We get A delta X. By the way, when I say delta X, this entire thing is a vector, delta X. Right? This is the same notation we used before. Plus delta A times X plus delta A times delta X. And all of that is equal to lambda X plus lambda delta X plus delta lambda times X plus delta lambda delta X. Okay. All I did was multiply out that expression. Hope you agree with me. Now, here's where some of our fuzziness is going to come in. Delta A, we're going to assume is small. And something I'm not going to prove to you guys, but it's kind of intuitive, is that if you only change your matrix a little bit, its eigenvectors can't change that much either. This is a fact you really should prove, but we're not going to. But in particular, we can say, okay, well, delta A and delta X are small, and their product is especially small, and we're just going to ignore it. And the same goes over here. Okay. I told you, so these things are going to get a little heuristic. So now we get this quickly. Alright. So if we do that, then what else can we do? Well, we know that lambda is an eigenvector, that lambda and x are an eigenvector eigenvalue pair, right? In particular, ax equals lambda x. So I can subtract ax from both sides, and these two go away. Yeah? And finally, we're left, let's clean up a little bit. So this is a delta x, right? Plus delta ax squiggly equals lambda delta x plus delta lambda x. A little bit cleaner. Okay. Now, what do we do with this? This still doesn't give us a condition number. It doesn't tell us how things are changing. This is kind of implicit looking. Anybody have any good ideas? This was non-obvious to me until I read Krylov and Van Loon. They showed me the light. Both of them. The trick is this. We're going to define something. Okay, right? In math, whenever you can't, you can't deal with the expression you have, you just kind of group it all into a variable you don't know anything about and ignore it. And this is going to be one of those cases. But it's slightly nicer. So, we're going to define something called a left eigenvector. And the idea is this. Suppose that ax equals lambda x. Right? Then, in particular, this, right, I'm sure you've seen this all before, right? A minus lambda I x equals 0. And if you're in Math 51 and you want to find eigenvalues, you take the determinant of this guy. But we don't like that because determinants are sort of numerically yucky. But in particular, because of this, because x is non-zero, what does that tell you about this matrix? It tells you that he's not full rank. Right? He has at least one thing in his null space, namely s. And I'm going to cite a theorem from Math 51. I checked, it's in your book. If a matrix is not full rank, then his transpose is also not full rank. It's a pretty reasonable theorem. So in particular, What is this? What does that mean? That means that A transpose minus lambda I, technically transpose, but I is obviously small. This thing also has something in his null space. We're going to call it Y. Yeah. So what did I just do? I showed you that there exists a left eigenvector Y such that A transpose Y equals lambda Y. Tricky, huh? So, for each right eigenvector, there exists a left eigenvector. By the way, why do we call it left? It's because if you take transpose both sides, it looks like Y transpose A. No? Yeah, so for each eigenvector on the right-hand side, you can come up with a corresponding guy on the left-hand side. So, this is going to be what buys us our condition number for eigenvalues. In particular, what we can do, this is going to look fishy for a second, and it should. We can go back to our expression here, and we're just going to pre-multiply by Y transpose. Yeah? We're going to do this. Y transpose. Cool? So, what happens when I do this? Well, first I get my notes back up, because I probably get it wrong. Okay? So, what is Y transpose A? Somebody say something. Y transpose A, what is it equal to? Lambda Y transpose. Lambda Y transpose. Thanks, Lambda. So, this thing is lambda Y transpose. Conveniently, that's here. Yeah? So those two terms go away. And what do we get? We get Y transpose delta A approximately equals Y transpose delta lambda x. Yeah, did I do that right? I think I did. Yeah. In fact, delta lambda is a scalar. Right, so let's put them on the left. Cool. Now, oh, oops. There's an answer. Told you this stuff is finicky. All right. So, what do? Well, now we can just divide both sides by Y transpose X, and this gives us our favorite formula, my favorite formula, for the perturbation of eigenvalues. Everybody needs one. And mine is that this is approximately equal to Y transpose times delta A times X, right? That's this guy, divided by Y transpose. Cool. Now, we can do slightly better than this, because what happens here, well, this is an inner product of Y, delta A, and X, and without loss of generality, we can assume that mod Y2 is equal to mod X equal to 1. Yeah? And it's kind of easy to see that this thing, in fact, is bounded above by just the Frobenius norm. I guess there's kind of an approximation there because we made a fuzzy approximation there. Okay. Or around the two norms, sorry. Okay. There's our bound.